Well, I tell you what, it's true. These P-Series, they don't know how beautiful they are. You're going to love these ones. And again, this will, no promises, but we're going to make a run at the record for shortest video here tonight. We might fall just a little short of that goal, but we'll give them a run for their money. Now, right now, your toolbox has a few elements in it. We've got your geometric series and the rules that go with them. We've talked about the nth term test for divergence. Again, it cannot be used to prove convergence, but it can be used to prove divergence, and that's very handy. And then we introduced you to a special type of series called a telescopic. So those are the three things. We're going to add a fourth element to that toolbox called a P-series today. And we've kind of been building up with this. Back when we did improper integrals, we kind of foreshadowed just a little bit, knowing that the P-series was coming. Okay, so here's where the foreshadowing took place. We were talking about the integral from 1 to infinity of things like 1 over x and 1 over x squared or 1 over x or radical x, things like that. Anyway, the integral is from 1 to infinity. We were trying to measure the area underneath the curve, and of course it was unbounded, and that led to a whole bunch of options. But anyway, I want to talk about, instead of 1 over x, we're going to call this graph 1 over n. So this graph passes through points like, 1, 1, 2 comma 1 half, 3 comma 1 third, 4 comma 1 fourth, etc., etc. And it continuously gets smaller and approaches the x-axis without touching it. What we're going to come to find out is we're going to call this equation the Great Wall of Divergence. That's the special name we give it. You certainly won't find that name in any official math textbook, but that's what we've kind of named it in our class in previous years. Now, what we have is we have certain families that fall above it and other certain families that fall below it. And we want to talk about ones that fall above it. Think of like 1 over radical x. It starts off inside, but then cuts to the outside. So this orange graph is like 1 over radical n, which is, of course, 1 over n to the 1/2 power. And so basically what we're saying is we have the black graph, which is the Great Wall of Divergence. He himself diverges. And then any graph that's above that black graph also diverges. And then we have a whole other family of graphs, such as 1 over n squared. They start here, they intersect at 1 comma 1 again, and they sneak underneath that black graph, okay, and they live within here. And so this might be something like 1 over n squared, and I'm going to run out of room and that's going to get very messy, and I'm sure you can't read that, but we'll call it 1 over n squared. So basically what we're saying is anything that gets underneath that black graph now converges. So everything in here is what we call convergent territory, okay? Anything that's above the black graph, those divergent. And that's basically the rule of thumb that we're going to live by. Oh yeah, one more comment there. What's kind of wild about all these graphs is that none of them do touch the x-axis, of course. So why do some converge and others don't? Well, it has to do with the rate at which they approach the x-axis. Some of them approach it fast enough that the terms get so small you're essentially adding 0, and then others just kind of, mosey along, take their time, and because they don't approach the x-axis fast enough, they never converge. So what does a generic P-series look like? Well, they usually come in this form. They usually like to start at 1, okay? And it's going to be 1 over n raised to the p power, okay? I'm going to shrink my pen here a little bit, make it a little finer tip. Let's see here. So that would turn out, so if we expanded it, that would be like we're substituting 1 in for n, and we'd get 1 over 1 to the p power. And just to remind yourself, like n's considered my variable, I guess. He's taking the place of what x used to be. And p is strictly a constant, okay? Strictly a constant. So anyway, back to substituting and expanding here. Then we'd substitute a 2 in for n, and then we'd substitute a 3 in for n, and a 4 to the p power plus ... 1 over n to the p. And then unfortunately, we don't have quite enough room, but we'll make sure, do me a favor, make sure you got your ... there after the nth term. So that's what it looks like. And here we're going to swoop in and we're going to talk about theorem 9.11 here. Okay? And basically, here's what theorem 9.11 says. It says, consider the generic P-series. All right, 1 over n to the p. There are 2 possible outcomes, basically, and they couldn't be any simpler than this. Number 1, the P-series is going to converge as long as p is greater than 1. And then on the flip side, we're going to say that that generic p-series is going to diverge as long as 0 is less than p, which is less than or equal to 1. Now, the seems so simple. Now, where we're going to probably confuse this, we're going to start to, hopefully not, but we might start to confuse it with the geometric series, okay? And just remind yourself, when we're talking about a geometric series, a geometric, just to compare them side by side, says we're starting at 0, and we've got a times r raised to the nth power. And we basically said in order for this bear to converge, we wanted the absolute value of r to fall between 0 and 1. Okay, and then we said it's going to diverge if the absolute value of r is greater than or equal to 1. So here's a couple of things to keep in mind. If your p-value or your r value is equal to 1, then it automatically diverges no matter what. Then after that, it gets a little more confusing. Basically, with the geometric series, you want your r values to be small in order to claim convergence. On the flip side, with a p-series, you want your p-values to be big or large in order to claim convergence. So it's kind of just the opposite, just flip-flop. But if you can visualize the generic form and what these look like when they're expanded out, I think it makes a lot of sense that you want r's to be small and you want the p's to be large. In both of those cases, what's happening is you're forcing your denominator to get bigger and bigger and bigger. And if your denominator gets bigger and bigger and bigger, then the fraction as a whole starts to get smaller and smaller and smaller, just kind of an inverse relationship. Well, we have one really, really special p-series that I want to introduce you to, and that looks like this. It's just very simple, okay? In fact, it's so simple you almost won't even recognize it as a p-series, but it is a p-series because the exponent on the n is a 1, so we would say it's a p-series with a p-value of 1. And as you start to expand this out, you get 1 plus a half plus a third plus a fourth plus dot 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 plus 1 over n plus dot dot dot. And again, just to kind of tie everything together, do you remember when we talked about the nth term test? And we said, the nth term said, the limit as n approaches infinity of this general term, and we ended up getting 0. And we said, well, just because you get 0 doesn't prove for sure that it converges. And in fact, we know that because the p-value is 1 and in fact doesn't converge, it actually diverges. So that's a good way of reminding yourself that that nth term test is inconclusive when it does equal 0. But anyway, I diverge a little bit. What I really wanted to talk about was this special series up here and how it has a really special name. We call this the harmonic series, okay, or the harmonic p-series. And it has a great story behind it, and I'd encourage you to maybe Google it if you're interested and check it out. But basically they said, back in the early days with when they had stringed instruments, they said if the strings within the instrument had lengths of 1 and 1/2 and 1/3 and 1/4, then that instrument produced harmonic tones. And that was just a really special case that they felt produced the most harmonic and harmonious music back in the day. And like I said, I encourage you to Google it and do your own research on it if that's something that intrigues you. Okay, we're going to dive into 3 examples here before we call it a night. And basically, we're just going to keep applying our rule. Let's see, we got 6 divided by the cubed root of n raised to the 4th power. And half the battle is just identifying and making that decision. They're saying, hey, this isn't just any old generic series. This is a p-series. And perhaps if we rewrote it, we could always pull the 6 out, kind of get that out of the way, just like we would with an integral. The same properties apply there, believe it or not. It's quite convenient. And 1 over, and I'm going to rewrite the radical with a fractional exponent. I'm going to say n raised to the 4/3 power. So anytime you have n in the denominator and he's being raised to a power, it's a p-series. And we could say, well, the p-value here is 4/3. Okay, and because that's greater than 1, we're going to say that this p-series does indeed converge. And just remember that we want big p-values because the bigger the p-value, the bigger the denominator becomes. And once that denominator gets large enough, the fraction as a whole is approaching 0 at a very fast rate. Okay, our next example, as I just started writing it here, they're not giving us the series in terms of sigma notation. What they're doing is they're presenting us with a series that is partially expanded already. And hopefully you can read my handwriting here. It's very important that you do. If you can, it's my fault. So they said 1 plus 2 over, or 1 over 2 times the cubed root of 2, and 1 over 3 times the cubed root of 3, etc., etc. So here's how they're going to present you with the problem. Now my advice to you is always, if it's not already in sigma notation, always rewrite it so that it is in sigma notation. So that's a very profound statement there for your notebook, that we always want to express it in sigma notation if it's not. And I think what this is, and remember back when we said, when we were looking for pattern recognition a few videos ago, and we said, well, that's, n equals 1, and n equals 2, and n equals 3, and so forth and so forth. Hopefully you find this to be a very easy one, but for instance, how do you transform a 4 into this specific term? And I said, well, that's not too bad. This is actually a very friendly one. It's actually n times the cubed root of n, which as you rewrite this, and you clean it up a little bit, we could add the exponents on the bottom and end up with n to the 4/3. And now we recognize it as a p-series, and we say, well, because p is equal to 4/3, and that's greater than 1, then this p-series will indeed converge. Here's another similar example in the sense that they kind of gave us the series as a partially expanded series, and it's our job to rewrite it in sigma notation first and foremost. And so we say, well, this is the sum of, let's see, we'll start it at 1, and it looks like it's going to be n divided by the 4th root of n, which right now doesn't look like a p-series, but what we could do is we could simplify it, and we could subtract the exponents. Whoops, back up, time out. I want to scratch that. My bad. I want to tweak this just a little bit. Okay, let's redo this. Let's call this number 3. Okay, let's say they said 1 plus, let's put the 4th root of 2 on top and 2 on the bottom, and then we've got the 4th root of 3 all over 3. My apologies, I goofed that one up. Okay, so let's say they presented it like this. And we could rewrite that in sigma notation as the sum of the nth term. We could say the 4th root of n divided by n. And we'll start to simplify that, which basically means we want to subtract the exponents. And an exponent of 1/4 minus an exponent of 1 gives us negative 3/4. And because it's negative, we're going to put that on the bottom. So it's 1 over n to the 3/4. Now you more accurately recognize it as a p-series. We say, well, the p has a value of 3/4, which is less than or equal to 1. And because it's smaller than or equal to 1, we're going to say that this p-series definitely diverges. The denominator is growing, but it's not growing fast enough to warrant a convergence series. So there's 3 examples. Hopefully you can memorize the graph, visualize the great wall of divergence, and the fact that anything that's above that graph diverges, anything below it converges, and just the simple rules for the values of p. All right, we'll see you tomorrow.